So, welcome to the simulated annealing video. This video follows the hill climbing video, so there's a bit of context probably needed from that video, so watching that one first would make this video a lot more helpful. So what is simulated annealing? Wikipedia defines simulated annealing as a probabilistic technique for approximating the global optimum of a given function. So that's just a fancy way of saying that we allow moves that are seemingly bad to our heuristics standards by starting very random on our problemscape and then slowly decreasing the randomness of our decisions as we go forward. So from the hill climbing video, we can remember that the idea of getting a kind of random spot may help us avoid local maximum and get us to the global maximum. In relation to the hill climbing video, this video will focus on how that optimization makes a better, well-rounded solution. So the annealing schedule. The annealing schedule is the maths and the algorithm that defines how we should decrease our temperature as we go along in the annealing process. So some dot points or main ideas of the annealing schedule is that our temperature must start at some value and then decrease to zero. With regular annealing, the temperature starts really high when the metal's hot, and then as it goes down to a room temperature. So when we're not making random decisions, our temperature is zero. So when the temperature does equal zero, it's common to implement a greedy heuristic at the end. So, once you're stopped picking the random decisions, you just follow the trend upwards with the hill climbing technique. And normally, the longer you let your annealing run for, so a longer annealing schedule means you'll get a better result. That's just a general rule of thumb. But it's not always feasible. It's not always worth doing because the longer you run, you're computing longer. It can take more resources, it can take more time. Sometimes you just want to pick a sweet spot of time. And as you can see on the right there, we've got two examples of a fast and a slow annealing schedule. So this is just an example from Wikipedia where the goal of the optimization software was to kind of align pixels with a similar energy field. So you can kind of just think of it as a metal lattice cooling down. And when it's done fast, the result isn't really good. And when you do it slower, the result works better, but it does consume more resources. We'll go through a pseudocode example. This is the example from Wikipedia. There's a lot of different ways to implement simulated annealing, and this is simply just the way they've done it. So it's more the concept that we're worried about in this video, but we'll just use this example. And then on the right, we'll play a video that will show how the pseudocode translates into kind of a problem-solving example and all of the different aspects of the algorithm. So starting off, this first line here, this is just setting our initial state. So S in this algorithm is our state. S0, S with the subscript 0, is the initial position. So back to our hill climbing algorithm, that is just picking a random spot on the problemscape we want to start at. And then this loop here, from k equals 0 through to k max, is just initializing each step. So k is our step number. We start at step 0 and we go for k max steps. So this is just a way of quantifying how long you want to run for. Do you want a high resolution or a low resolution? This is kind of our compute time. And then in each iteration, each step, we assign T here as our temperature. And this temperature function here is accessing our annealing schedule. So this argument here doesn't really matter for this example, but what this will do as K increases, our temperature will decrease. So it's just giving a temperature from our temperature, it's getting a temperature from our annealing schedule. And then with that temperature, and our random neighbor, which is a random spot around where we currently are, if a probability of that spot dependent on the temperature matched with some random probability, if that's true, we pick a new spot. So in essence, all that is doing is saying, let's pick a probability with our temperature T. If the T is really high, our probability for picking a new spot is also high because that's how simulated annealing works. We want to accept more random spots with a higher probability. And if that's true, we pick a new state. So I'll compare it to our video here and it'll make a bit more sense, hopefully. So this video here is doing the traveling salesman problem. You can see here, our probability starts at 1 when the temperature is really high, as you can see over here. And then as the temperature slows down, our acceptance probability also goes down, which means we're not accepting such random spots. We start to follow some sort of trend. You can see now that it's only making little changes with such low temperature. And then we arrive at a more optimal solution than we started with. and some conceptual examples to kind of help remember what simulated annealing is about. We can use Tony Stark as an example. So when Tony Stark started off in the Marvel Universe, he was really sporadic, and he was labeled as a playboy. He was doing things that were quite random, and there wasn't much decision to it. And then as his temperature cooled, as he went off to Afghanistan in the movie, and he was under terrorist occupancy, spoiler alert, he slowly made less sporadic decisions, and he kind of cooled towards a global maximum, which was his well-rounded hero character. So he was really sporadic at the start, and then he slowly made his way to the global solution. And Linus Torvalds as well, and Linux in general. When you're making code, you start very general, and you can make massive changes early on. And then as you cool and you've done more work, you'll only be making little changes. So they're just two ways of kind of remembering how to remember the simulated annealing. When do we use simulated annealing? So simulated annealing in a heuristic and computation scenario is when you've got an optimization technique or method that can get stuck at local maxima. The whole point of simulated annealing is really to avoid local maxima in conjunction with another heuristic method. And as we saw in the hill climbing method, that is quite common to get stuck at local maxima. Relating to specific problems, we have the traveling salesman problem and the graph coloring problem, which are both NP hard problems. So that means that we can't really get a perfect solution without checking the other solutions, which is an NP hard problem. And using this optimization technique, we can kind of explore the blind problemscape and to find a global maximum. And we have an example here. This is the 2019 VCE Algorithmics exam. And this was a very difficult question, apparently. The average mark was 1.4 out of 4, but I think you guys can do pretty well at this, considering the simulated annealing technique we've just discussed. The question outlines Donna, who has a number of forms numbered 1 to 5, and she needs to deliver each of these forms to a classroom. And they've given an example table here. Donna would like to deliver each of these forms in the fastest way possible. So with that simple information there, we can abstract a little example. I'll let you guys think about it, and then I'll give you the solution. So then kind of like a pause there or something. And then, so going over the answer here, we've got quite a brief explanation I've screenshotted here, but the main idea of this was to abstract away from the actual table example and think. Donna has items that she needs to deliver to different spots, and she wants to do it in a quick way. Thinking about traveling salesman problem, that is a direct correlation. So talking about how you could use the traveling salesman problem to solve that example was what they were looking for, but specifically justifying how to solve the traveling salesman problem in a meaningful and effective way. So because it's NP hard and she may have a lot of classrooms to get to, using a heuristic would be the correct approach, because you're going to use a lot of computation time if you're doing it brute force, but the heuristic is used to kind of get an optimal solution in a reasonable time, which is the simulated annealing method. So some limitations and advantages about the simulated annealing method is that normally it's designed to forget its solution history. So that's similar to the hill climbing method. But not remembering the solution history is normally good, because the algorithm is designed to work without needing to backtrack on its old history. So because we're not storing each part that it's checked and going back and checking those values, we're saving a lot of computation time, and the algorithm's designed to work around that anyway, so it will tend towards a good solution without needing to backtrack. And an advantage over other heuristic optimization methods is that it's less likely to get stuck at local maxima. So we can use that fact to get more of a global optimum rather than just chasing the local maximum each time. So to conclude this video, some basic notes that you should remember and note down for your exam is that simulated annealing allows a heuristic to approach an optimal solution by exploring those suboptimal solutions early on and then trying other solutions around the problem scale. And your annealing schedule, so that's just that when you decrease really quickly in temperature, you'll get there quicker, but it probably won't be a good solution. And on the contrast, if you do it slowly, you'll probably get a better solution, but it may take longer. And the important one is that simulated annealing by itself can't guarantee you the correct answer. You'll have to use it in conjunction with something else. If you're using an NP hard problem, you'll have to find every solution. If you're doing a simple problem, you can use some sort of validation, but simulated annealing by itself can't exactly give you the guaranteed solution every time. And it's mentioned a lot. In most of the exam reports I've seen, they've mentioned how simulated annealing could be used to justify your solution. And I think it's definitely worth noting and making sure you got this one down for the exam. Thanks, guys.
What's going on? You were going to tell me you really were dying? Why didn't you tell me that?
Hey, save it for the honeymoon. You got incoming, Tony.